Okay. I think I am ready. Are you guys ready? Blake, so we'll start with our same bat time, same bat person.
Do you mind doing number 33 from 611?
No, man, that's fine. We can do that. All right. 33. All right, so here it says, use a graph to find the appropriate x-coordinates of the points of intersection of the given curves, then find approximately the area of the region bounded by the curves. Why does it have this extra approximately here in parentheses? Well, it's because you're rounding the decimal from your calculator when you put it in, plug it into your integral. So it's going to be an approximation anyways, whether you do the integral on your calculator or if you do it by hand. So let's just start by finding those points of intersection, because this is not one that I would want to try to do by hand, and it probably is not possible to set x times sines of x squared equal to x to the fourth and get anything out of that. I mean, 0 I can see is going to be a solution, but you know, I'm not super interested past that. I don't really know what to expect here. I'm just going to start with pi over 2 to negative pi over 2. Because I don't really know what I'm going to get out of this, but we'll start with that and see what happens. So here's my first one. This is x times sine of x squared. There's that one. So it looks like any intersection that's going to be happening is happening in here next to the origin. So we'll zoom that in a skosh. Probably just make that negative pi over 2 to pi over 2. And then maybe negative 1 to 1. Okay. Well, that's Mr. Kulik. That makes much more sense. It's like, why is this seem so strange? Okay, so I have an intersection here at 0, and then I have another one happening over here, right? All right, and I could zoom in some more and get a better picture, but I frankly have enough. So first curve, second curve, and then guess. I have to be careful about the guess because there's more than one intersection. So I actually have to move that close to where I'm looking. So 0.896 is what we'll call that. And then did we remember which one was on top? There, let's look at that picture again. I think it was the sine squared, or sine of x squared was the one on top. So there's that one. Oh, I know what to do. Maybe that is the bottom. We'll do that and just make that a thick line, and we should be able to tell.
Yeah.
Oh, I didn't make it visible, did I? Yarg! And I pressed the thing, and it decided to jump to the other side of the screen because that's an option somebody was asking for. Okay, so that was the top, the sine of x squared. And now this is something I can do by hand, right? We can do that integral by hand. Do you guys agree?
Yeah.
So I'm going to be doing a u substitution in the first one. So we're going to end up with that the integral for sine is negative cosine. And I guess here I probably should have, we're going to just drop the u back in because I'm not going to do a substitution for just one of these. Oh yeah,
I know we can, but like.
Yeah, we can do this. And then from here it's just plug in and chugging, right?
Yeah. Okay.
Just to re-establish how you would go about doing this. So I've already entered these into the y equals.
Yeah.
So I do math function integration from 0 to 0.896. And we had y1, vars, y vars, function y1, minus y2, vars, y vars, function y2, respect to x. And there's my area, which is probably expected if we looked at the picture. There wasn't a lot of space in between those.
Mm-hmm.
So about 0.037.
Isn't there a command on your calculator that can have you do difference, like the difference of two integrals, like you just plug in, like, and you don't even have to find like an intersection point or bounds in it or anything? I don't know. Probably not. Maybe it's probably on like the TI Inspire or something.
Yeah, it might be a CAS function. I'm trying to think if there's something hidden here. I don't know. I've never played around with like whatever this function is. Like integral of f of x, I imagine is something, but I don't know that it.
Yeah, it's probably a yes.
Yeah. But that's that. Again, I went to here to just show you that we can do this by hand, and then I just typed in the calculator to actually get the decimal because it was going to be about the same amount of work to type this with the substitutions in as it was going to be just to do the integral. So you're happy with that though, Blake?
Yes. Very.
Okay. Mackenzie. Number 11. Sure. Okay. Ugh. All right, so a lot of directions here. It says sketch the region enclosed by the given curves. Decide whether to integrate with respect to x or y. Draw the typical approximating rectangle, label height and width, then find the area of the region. So we have this guy. So we'll start by graphing this. Because maybe it's not entirely obvious what even the graph of this is going to look like. Anybody can take a look and tell me what the graph is going to look like? Yeah, they're going to be sideways parabolas, correct? Good. So if I pick the first one, if I pick a value for y, say 0, then my value for x would be 1. If I pick the value for y to be 1, my value for x would be 0. If I pick y to be -1, my value for x would also be 0. That's enough for me to get a picture. Similarly over here, if I pick y to be 0, x is -1. If I pick y to be 1, x is 0. If I pick it to be -1, x is 0. So that's kind of enough for me. So I'll do this one as an orangey and this one as a bluey. So I have 1, 0, 1, -1. So there's the orange parabola. The blue one's -1, 1. There we go. Blue. And so we're looking for that region between them. Does that feel okay there, Mackenzie? Okay. The next asked us to decide whether we should integrate with respect to x or y. What do you want to do on this one? There's a classic example. I want to hear what you think. Okay, so you should, because one way is much, much easier than the other. So you should pick y. The reason is that if I look with respect to y, the orange function is always on the right of the blue function. If I look with respect to x, the blue function is underneath the orange function, and then it switches at 0. So that's going to make the integration like a lot more complicated because you're going to have to be really careful setting this up. I want to integrate with respect to y because I don't have to worry too much about the setup. So the rectangles we're building are like here. So the width there is like dy, and the height would be the one on the right minus the one on the left. Everybody's okay with that? So we're going to integrate. This is the start of my integral, right? This y-coordinate, which was at 0, -1. And this would be the end of my integration, 0, +1. So we'll integrate with y's, -1 to 1. The function on the right minus the function on the left, dy. And again, they have to be set equal to x in order to plug those functions in to integrate with respect to y, but they already were in the problem. That's another good indicator that, you know, that this is be what you'd want to do. If we simplify things down inside there, we end up with 2 minus 2y squared. So we can pull out a factor of 2. And if you wanted to, you might notice that 1 minus y squared is an even function with bounds that are opposites. So if you wanted to, and I would do this, I would just do 4 times the integral from 0 to 1 of 1 minus y squared dy. Now it saves me just a little bit of time because when I'm substituting in 0 is way easier than anything else, right? That's the ideal bound to have on an integral is a 0. Do you need to do that trick that I just did though? No, it's just like a little time saver. Good. So we'll do our antiderivative. I guess like that. So 1 minus 1/3 is 2/3 times 4 is 8/3. Can I still do this on my calculator? If I wanted to do the function integration? Yes. What would I do? I would set it up exactly like it's written, except instead of y's, I'm just going to type x's, right? Because we know the name of the variable doesn't change the integral. So 0 to 1, oops, I forgot the times 4 out front. Let me sneak that in there. And I'm not going to bother typing this in. I'm just going to do like 1 minus x squared dx. And we notice that that is, if I turn that into a fraction, 8/3. Kenzie, does that feel okay? So the big takeaway, the picture really informed me a lot in terms of whether I want to integrate with respect to x or y. In general, if I see something where I have like endpoint to endpoint, or intersection to intersection is on the y's, that's telling me that, like, please integrate with respect to y. Will be massively easier for you. As opposed to if I look at the points of intersection have nothing, I mean, it's the x coordinates are meaningless. You know, integrate from 0 to 0 on x, that doesn't help. And that's, I think, in terms of this section, I think that's the hardest single skill, is to look at the thing, be able to get a graph out of it, decide how to set up the integral. The integration itself has been pretty easy, right? The hardest part has been like choosing whether do I want to integrate with respect to x or y, or finding the intersections, or getting this thing all set up, you know, doing a little Mr. Kulik trick to make the integral even a little easier to deal with. But the actual act of integration is pretty easy. Nothing super tricky there. What else you guys got? Blake?
Do you mind doing number 50?
50? Sure. I'd been surprised if we were going backwards a section or forwards a section. That would have been a real surprise. Yeah, it's like, I'm there. So find the area of the region bounded by the parabola y equals x squared, and the tangent line to the parabola at the point 1, 1 and the x-axis. Okay, so first thing I'm going to do is find the equation for the tangent line. So the slope for that tangent line is going to be the derivative of x squared evaluated at x equals 1. So the slope is 2. So if I write my point slope equation, I have y minus 1 equals 2 times x minus 1. I distribute through my 2 and then add over my 1. And there's my equation for my tangent line. So if I wanted to sketch a little picture of my graph, we'll do the tangent line in orange, and we'll do the parabola there in blue. everybody's good with like me not needing to generate points to do that, right? So like 0, -1, and then we'll go 1 over and 2 up. Grab the ruler function here, get a nice straight line. Okay, that's good with that. And then the parabola y equals x squared, so I have 0, 0, -1, 1, +1, 1. That's not super helpful in terms of seeing where that air region is. So let's do this. I'm just going to set those things equal to each other. Oh, never mind. I'm dumb. Why is it not worth doing this? It's a tangent line. It's only going to intersect one place, right? So it's like that is how my graph should look. Okay, so we want the area of the region bounded by the parabola and the tangent line to the parabola and the x-axis. So the x-axis is here. So what are we talking about? This little spot right there. Everybody agree with that? Okay. Should we integrate with respect to x or y? That's fine. Yeah, that's fine. I think that's fine. So we're going to do dx's, and we're going to start at 0 and go to 1. And the parabola is always on top. So we're doing that, right? Okay. So that's going to be x squared minus 2x plus 1 dx. That's an easy antiderivative to do. So x cubed over 3 minus x squared plus x evaluated from 0 to 1. So that's 1/3 minus 1 plus 1 minus 0. So we get 1/3. Mia? I think y would have been fine. So, yeah, so if we did y's, again, we're starting at 0 and going up to 1. And the one on the right is 2x minus 1 minus the one on the left. So if we do that, we'd have 0, 1, negative x squared plus 2x minus 1. Oops. Huh? Well, because it's always the right curve minus the left curve when we're doing y's.
Yeah. No, I mean next one over.
I just rearranged it.
Oh.
So I just put it in standard form. That's all I did there. That's okay. And now when I do this, oh, thank you. What do we get here? We get negative 1/3, plus 1, minus 1, minus 0. Somehow we have this in the wrong order, because now we're just getting a negative 1/3 here. What did we goofied up? Oh, I know why. I know the problem. What? Well, I mean, that would take care of the negative sign if we did 1 to 0, but why would we be doing 1 to 0? Well, that's just to like close the region. If it wasn't closed by the x-axis, then this would be, like our area would be like infinite, right? Like it'd be all that junk, right? We need the x-axis to like close the bottom. I'd have to think about that, Mia, where I'm losing that negative sign at somewhere. If we tried to do with respect to y. It's not entirely obvious to me right this second.
Wait, but how do you account for like the bounding of the x-axis when you're derived, like when you're doing the integral of with respect to x?
Well, it told me the stopping point.
Yeah, but isn't it like the stopping point is like the value of 0, and isn't there that whole extra triangle underneath?
There you go. That's the issue. Yes. Thank you, Blake. Yep, you got it. Nailed it. So that's the issue, Mia, is that if we did y, we're also counting that region, right? No? Well, if you think about it, we're going from y equals 0 to 1. So like this part is still, like cutting off at 0, that part is still below, like it just, yes, that's the issue. So
Wait.
You don't want to.
Okay, so but when you're with respect to y, you're going from 0 to 1. That little bottom triangle would count.
Oh, yeah,
from
yeah.
0 to negative 1. That would only count when you're driving with respect to x, because 0 is just that whole vertical line, is like the whole y-axis itself over to 1, which includes that little triangle. Yeah, but y wouldn't.
Right.
Which doesn't make sense because you got a negative integral from with respect to y.
Well, it's an even, and I'm not in my classroom with either my worked out solutions that I did by hand or the answer book. I guess I could run across the hallway real quick. It's not fine. We want to know the answer. I want to know the answer. I'll be right back. Let's get a second.
Let's party. Yes. Which was this? Question 15? Okay, so the answer was neither. It was 112.
Where's Paul? I have a question for you. Yeah, can you pick a number 1 through 100? 94? Thanks. That was it.
Yeah, this is question 50, right? Correct?
I know, right? Okay. Got my book. Blake, do you have the answer book too?
Maybe.
It's okay. I don't care.
I'll tell you, it's neither of those answers though.
Oh, that's even better. Makes me feel so much better that I'm teaching the class and I can't do the homework problems, right? Ugh. What is the answer?
It said 112, but I don't actually have the official answer book, and the answers have been wrong before.
Okay.
So I'd still take a look.
Oh my gosh. Okay. All right.
Different variables.
Okay. So, bye-bye to all you guys. And we'll go ahead and just do that.
So
All right.
you have to derive, or you have to integrate.
I think that would be the better option, yes. We'll talk about in a minute why going with X is going to be a problem. But I think you already kind of nailed it. So first thing I'm going to do is rewrite y equals x squared as that. And then what do we have? We have y equals 2x minus 1 turns into y plus 1 over 2. Now I feel like some good stuff is about to happen. Now, I'm going to discard the minus from the plus or minus. Why am I doing this? Because the region we're talking about is above the x-axis. So the y-coordinate has to be positive. Now I feel better. Okay. So integral from 0 to 1, I'm going to rewrite this as y over 2 plus 1/2 minus root y. Or, well, we'll even write it y to 1/2. So if I do my antiderivative now, I end up with y squared over 4 plus y over 2 minus 2y to the 3 over 2 over 3, evaluating from 0 to 1. So I have 1/4 plus 1/2 minus 2/3, and then all minus 0. And that's going to be, writing those, common denominator would be 12, so 3 12s plus 6 12s minus 8 12s is 1/12. So there we go. And again, if we wanted to do this with x, that's the problem, is we have that part that we'd have to subtract away.
But we still did the x thing wrong, because
yes,
1/3 is larger than 1/12, so you can't possibly have, like, that can't possibly be correct, because if you're counting for that negative space, it has to be less than 1/12.
Mm-hmm.
So, well, I mean, it doesn't even matter because that's not correct. That, like, we can't do that. So.
Well, here's why it's more, like, is that we're subtracting the integral that's going to have the negative part to it.
Oh,
that's why it got bigger.
Makes sense.
Yep. I was like, nope, I'm like, that is, yeah, there's got to be a reason why that's bigger. And that was it. There we go. We got it. We did it. It was worth me running over there for a second, right? Plus, you got to see some visitors. That's always fun. All right. Should we talk here, start talking about 7.2 or 6.2 then?
I don't have two more. I'm sorry.
That's okay.
Done as.
All right. So in 6.2, we're going to be talking about volumes. So in 6.1, we did the area between two curves. In 6.2, we're going to be talking about volumes. So just as a little geometry review for us, if we have like any right three-dimensional shape, the formula for the volume is basically the area of the base times the height, right? So whether that is an irregularly shaped base, like this weird semicircle base, or a cylinder where the base is a circle, or a prism where the base is a polygon, it's just area of the base times the height, right? But what if the shape is like really irregular? Like this region or this shape here. How could we approximate the volume for this shape? What we'll do is we're going to slice these into little tiny cylinders where the height of the cylinder is so small that the bases are now basically regular, and calculate the volume of that little tiny cylinder, and we're going to do that all the way up our shape, right? We're going to just slice it into little cylinders, calculate the volume of those cylinders, add them all up, and if we make them infinitely small or infinitely thin, we're going to come up with the exact volume, right? In a calculus sense. That's what we're doing. So here's what we did. We did the sum from 1 to n of AXI delta x. So the delta x is the infinitely small width of our cylinder, and A of x is the cross-sectional area for that slice. So we know that if we then take that to be infinitely small, so the limit of n going to infinity, that guy will just turn into an integral. So our integral from a to b of the area function, or area for the cross section, dx, that's what we're going to do. All right. Let's say we want to do the volume of a sphere. Now, we know what the volume of a sphere is, right? We know it's 4/3 pi r cubed. Let's use calculus to end up deriving that. So, looking at the picture I've given you, what is that cross-sectional area going to be? Well, not r. What's the radius in this case? Y. But we want this to be A of x. Right? So how can I rewrite y in terms of x? What other shape do you notice is drawn into the picture here? A right triangle, right? So how can I relate y to x using that right triangle? Well, like, that's the point x, but this whole side has length x, right? That's just the value x on the x-axis. That's why they put a point there, but really that whole side length is x. So we can say y is then the square root of r squared minus x squared. Why did I dump the plus or minus there?
It's a distance.
Because it's a length. Yep, we're using it as an area. So the squared will cancel the square root anyway. So even if we had kept the plus or minus, as soon as we square it, that eliminates the plus or minus anyways. So there's my area function. Now let's start our integration. Okay, this is going to be a of x dx. So what are going to be the bounds of integration? What's going to be my a and my b for my integration? Which axes should I be looking at?
R and negative R.
The x-axis, so we're starting at r, or negative r, and ending at positive r. Very good. Everybody's cool with that? Again, since it's dx, we're looking at the x-axis for our bounds. Everybody's good? Okay. So if I plug in now the value for my area function, or the pi times r squared minus x squared dx, what's the antiderivative of r squared with respect to x?
R squared x.
Yep. And then the antiderivative of x squared is x cubed over 3. And we're just going to evaluate from r to negative r. Let's save ourselves some hassle here. What do you notice? Yeah, let's take advantage of that. That'll make the evaluation a little bit cleaner. Not that it wouldn't have worked with what we're doing, it just would have gotten a little yuckier. And my days are already yucky enough with this whole heating situation, me running around the building for a day. So I'm going to take my wins where I can get them. So I have r to the third minus r to the third over 3 is going to be 2/3 r to the cubed. And then 2 pi times 2/3 r cubed is going to be 4 pi r cubed over 3. What was the hardest part? Getting the cross-sectional area function, right? That was really the trickiest piece. After that, it was not so bad. The calculus piece was actually pretty straightforward, right? The antiderivatives and everything, when the integration was pretty easy. The setup was the hard part. All right, let's do another one. So this says find the volume of the solid obtained by rotating about the x-axis the region under the curve y equals square root of x from 0 to 1. So that's what I've graphed here. And then I spun that around the x-axis and I've created this like dome shape. This is where having some good three-dimensional imagination becomes really helpful, just for building some intuition of like closing your eyes, picturing what that's going to look like when it spins around. Oftentimes will be quite helpful for us. Blake's like, crap.
No, this reminds me so much of like the CAD class that this blue I teach.
Oh, sure.
Yeah, it brings me right back. I love that class.
Sure. Maybe it's not oh crap. Then it's like, bingo, I got this. All right. So when we've done our rotation here, what do you notice the cross-sectional area is? What shape is that? Well, it's a circle, right? The cross-sectional area, yeah, we're building cylinders with it, but it's across, the area is a circle, right? Okay, what's the radius of that circle? It's root x. So pi root x squared is our area function, right? So to calculate the volume, we're going to integrate from 0 to 1 pi x dx. So that's going to be, can pull the pi out front. The antiderivative of x is x squared over 2. Evaluating from 0 to 1, I end up with pi over 2 minus 0, or just pi over 2. How was that?
That's the whole area, that's the whole volume.
Yep. It's not a very big shape. It's just going from 0 to 1, right?
Yeah.
The height is very small. It's just 1 unit high. But that's the volume. Yep. Does that feel okay? Again, the hardest part is figuring out the area function. Now I'm being very nice by giving you these beautiful pictures. When you don't have the beautiful picture, we have to see that picture in your mind. It gets a little bit harder. All right, let's do another one. So it says, find the volume of the solid obtained by rotating the region bounded by y equals x cubed and y equals 8 and x equals 0 about the y-axis. So that's our shape on the left, right? As I've bounded it by x equals 0, that's the y-axis. Y equals 8. So just the blue region here that we're shaded in is what we're going to be rotating. And we rotate about the y-axis and we end up with, like, I don't know, looks like the tip of a finger or something. It's the kind of the shape that we have there. The cross-sectional area there, though, is what shape? It's a circle. The radius for that circle is, it's x. What's the catch, though? If we're going to integrate, then what are going to be the bounds of integration? Not entirely clear, is it? What if we integrate with respect to y? What would the area function there be?
You still use.
Oops, this would be like pi x squared. So the radius there in terms of y's is going to be x, or y cubed, or cube root of y, excuse me. Oops, and it's not 0 to 1, dum-dum. What's the upper bound there? 8, of course. And now that's a really easy integral to do, correct? Could I have done this still with respect to x? Hi, Miss Morgan. I have no heat in my room, so they've moved me here for first
Perfect.
hour.
Perfect. I'm glad to see some faces.
Yeah. Now, could we have found these bounds? Sure, it would have meant figuring out this intersection. So that would be plugging y in for, or 8 in for y, which is not impossible, but like, you know, yeah. Just a little bit easier. And then we have trouble like getting a lid on that then also, right? Because if you just did this, it would continue going up forever because you don't have a lid on it after you've rotated about the y-axis. Anyways, antiderivative. So we have y to the 5 over 3, 3/5 evaluated from 0 to 8. So 8 to the 5/3 is 2 to the 5th, so 32. No. Oh, because I forgot to multiply by 3. 96. There we go. As a hint, in general, if you're rotating about the y-axis, probably want to integrate with respect to y. If you rotate about the x-axis, probably want to integrate with respect to x. Is usually the vast majority of the time it would be the preferable option. So that's nice at least, right? That in general, that's some place to start. Because oftentimes, again, that stuff is the hardest part. All right. So here, the area R enclosed by the curves y equals x and y equals x squared. And we're going to rotate that about the x-axis. So what kind of shape are we going to get? Kind of like a funnel, but it's not going to be a uniform funnel. It's going to like be bowed in the middle and then like get skinnier at the top and the ends. Woof, right? So the cross-sectional area for that is what we've drawn here. So how do I write the equation for a of x for that? So the outer radius is x, right? So it's going to be pi x squared minus, pi x squared squared. The inner, so this is the area for the outer minus the area for the inner.
Although I feel like wouldn't that create like a negative number because...
Not if we're going from 0 to 1, though. Remember, like look at where the x values that we're going from. So
I see,
from 0 to 1, x to the 4th will be smaller than x squared.
Yeah.
So we're good. It won't be negative. I know. You look at that and you think that feels wrong, but it's not. It's okay. All right, so there's my area function. So we'll integrate from 0 to 1 along the x-axis. So intersection to intersection. And then we have this pi x squared minus pi x to the 4th dx. Can pull our pi out front. I wasn't going to say anything.
What do I live in a barn?
It's your barn though, right? we'll do our antiderivative. So we end up with 1/3 minus 1/5, and then minus 0. So what that's going to come out to be 5/15 minus 3/15, so 2/15, and then we have the pi still. Oops. Oftentimes we'll call this one the washer method if there's a hole in the middle of our function, because we're not building cylinders anymore, we're building like a washer. So far, so good. It's okay. Again, the trickiest part is the setup. Once you have the integral set up properly, the integration has been pretty easy, right? It's just been set up. All right. Here we go. What do you notice I'm not giving you here? Picture. Now, you're lucky because this one is just referring to the previous example. So you have this piece at least. I didn't make those separate. Let me just grab that then from there and drop it in. So we have that. So it's the same setup. But this time we're rotating about the line y equals 2. So like you're spinning it around that. What are we going to make there?
Kind of the same kind of funnel, but it doesn't connect.
Yeah, you're going to have a hole at each end, right? A small hole at this end and like a big hole at that end. And it'll be kind of like funnel shaped like that, right? You guys can see that. Again, closing your eyes, trying to think about it in 3 dimensions is like really a very helpful skill to have. So like thinking about that is a good idea, and taking some time to really practice that while you're doing the homework is, I think, really helpful. So let's go ahead and drop in what that picture is going to look like. So there's my drawing. So my cross-sectional area is this washer. Now this is the tricky part here. The outer radius is the distance from 2 down to the outer rim, right? That outer rim is the function y equals x squared. So it's going to be 2 minus x squared squared, well, pi times. And then the inner radius is going to be starting at the line y equals 2 and going to the inside function. That's y equals x. So 2 minus x squared. Everybody okay with that? We're still going to be integrating from 0 to 1. We're still going to be going along the x-axis. Well, it's still just the area formed by the intersection of the 2 curves, right? So this happened at 0. It's ending at 1.
Oh, oopsies. Yep, I see.
Mia. Yes. So if we're looking at the picture, so we have, here's the line y equals 0. That's the center of our washer. We're looking at the distance from 2 to the outer rim. If I go back and I look here, that's this distance. So starting at 2 and ending at x squared, we're subtracting this distance from 2. That distance is x squared. And then, so that's the outer radius. The inner radius is the same idea, but we're going down to the first function. So we're taking 2 and subtracting that distance, which is x. Because that y coordinate is like y equals x squared, or y equals x. Is that, you see it now? Again, it'll get easier once you've done some practice. It feels very foreign right now, and that's okay. All right, how do we want to do this integral?
Probably just
Yeah, absolutely, Blake. Good job. Yep. Foil this bad boy out. There's no u substitution to get around having to do it. You just got to do it. So I did that. I foiled it out and I distributed the negative through. So I did that all kind of in one step, just in my head. Feel free to take many more steps than that if you need to. So if we combine some like terms here, some good stuff happens because we lose those 4s, right? That helps a little bit. So we have x to the 4th minus 5x squared plus 4x dx. We do our antiderivative now. Let's do that. 0 to 1. So we have 1/3 minus 5/3 plus 2. And then minus 0. Oh, and we still have times pi. So, I'm sorry, that's 1/5, not 1/3, dum-dum. There we go. So let's see, that's 3/15 minus 25/15 plus 30/15 is 33 minus 25, that's 8/15. There we go. Is that okay? Again, setup was the hard part, right? All right, we're going to take that same region, but this time we're going to rotate it about the line x equals -1. So where is x equals -1 at? It's like here, right? So when we do that, what kind of shape are we going to get? You're going to have like an opening here and like a big opening here. You kind of curved on the outside. Oops. I move my window there. But it'll be like, the inner rim will be like a straight. It'll be kind of like that. Everybody's okay with that? So if we draw this kind of away from things, so this is x equals -1. Then we have our I guess we should do it like that, right? So that's like my inner radius. And then like this would be like my outer radius. Everybody's okay with that? Since we're rotating it around a vertical axis, we're probably going to be integrating with respect to y. So I want to write my area function as an a of y. Okay. So the inner, this function here, oops, give me that still, is y equals x. So my inner radius is going to be, Mackenzie? That's just some cross-section. Okay, it doesn't necessarily have to be anything in particular, just some cross-section. Is that okay? Okay. So what is that inner radius going to be? Keep in mind that like you have like the y-axis coming in right here, right?
So wouldn't it be like 2 minus x?
It'll be 1 plus
L1
x. Let's actually write the outer like this. So my outer radius is going to be 1 plus that distance, which is x squared. But we want this, we said we were going to integrate with respect to y. right? So I don't want x's in these. Now this one's easy because the equation is y equals x, right? Here we know that y equals x squared. So x is just the square root of y. And again, if we looked at our picture, all of this is above the x-axis, so I can drop the plus or minus and just leave it as square root y. So my area function for respect to y is going to be the outer, or I should say pi times the outer radius squared minus pi times the inner radius squared. And we're going to be integrating from y equals 0 to y equals 1. And then from there, it's FOIL these out, combine your like terms, yada, 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 integrate up. We're out of time, so I'm just going to cut straight to the chase. So that's just pi over 2. We still have a couple more examples to do in this section that I'd like to do, but you guys should be able to start on things. So the assignment is 1 through 17 odd, and then 31 through 33 odds. I would probably, if you got through 1 through 17, I'd feel pretty good. I'd probably stop at that point and wait to see the next set of examples before trying to go any further.
1 through 17.
And then 31 through 33, all odds.
Oh, okay.
Yeah.
It's like,
No. That's a lot of integration or a lot of setups to do. The setup is the hard part.